Welcome to the sixth course of the optimizationcity.com. Today we are going to explore something called shortest path problem. It's really interesting concept that involves finding the quickest or the most efficient route between the different places on a map. This problem comes up in lots of real-time situations like planning travel routes, organization, delivery system, and even just finding the shortest way to find your friend's house. It's like solving a puzzle to find the best path and to save time and effort. So get ready to the world of the shortest path problem. So what is the content table of content in this course? We have the four parts. In the first part, we talk about the minimum cost flow problem as a general form of the network optimization. In the second part, we tell you the algorithm of the shortest path problem. There are two types of network we discuss in this course. One, the loopless, and the other is loop network. Each section explores an introduction, key concept, and lots of examples. In the minimum cost flow problem, we want to distribute the same type of the product from the factory to sale market efficiently. We know that the quantity of product produced at each factory and the required quantity at each destination. Instead of sending a product directly to the destination, we can send them to the distribution center with the intermediate here to node 2 and node 3 point if needed. However, there are limited on how much can be transported on each transportation line. The objective in this problem is to minimize the cost of transporting product subject to meeting the demand. Look at the simple example of minimum cost flow in this figure. The nodes are shown on the number circle and the arc are represented by the arrow. The arc have a specific direction here, for example, from 1 to 2, meaning the material good can be transported from one node to another in that direction. For instance, we can send the material from node 1 to node 2, but you cannot send the material from node 2 to node 1. We use the notation ij that to indicate the arc going from node I to j. In this figure, each arrow represents a path with a specific capacity here. This is here in this 15, and the cost for transportation. This is $4. The capacity indicates the maximum amount that can be transported along the bad path, while the cost per unit represents the expense associated with each unit of transportation. For instance, for arc 2 to 4, the flow can range from 0 to 4, and each unit passing through this path costs $2. The second component in this parenthesis. The symbol infinity here for arc 2, 3 indicate that there is no limit on the capacity of that particular line. Moreover, the number in the parenthesis next to the circle represent the available supply and required demand at each node. In this diagram, the node 1 is a starting point and with the supply of 2 units, and node 4 and node 5 are the destination that require 5 and 15 units of supply respectively with the negative sign. In the minimum cost flow problem, our objective is to discover the flow pattern that incurred with the minimum cost. To formulate this problem as a linear programming model, let's consider the following example. Xij represents the quantity of unit transport from node I to j. Right now, we can present the linear programming of the minimum cost flow problem as follows. This is the objective function. We are going to minimize the objective function, which is the summation of the cost associated with for all arcs. Equation 1 to 5 represent the balance equation in the network. Let's consider the balance equation at node 1. This equation states that the combined flow leaving node 1, which is x12 plus x13, should be equal to supply available in node 1, which is equal to 20. This ensures that the outgoing flow match the available supply. So here, this is arc 1, 2, and 1, 3, and the flow after these two arcs should be equal to 20. Similarly, the balance equation at node 2 indicates that the incoming flow to node 2, which is equal to x12, is equal to outgoing flow from node 2, which is equal to x23, x24, and x25. This ensures that the flow entering and leaving node is properly balanced. There is no supply and demand in this node. So the minimum cost flow problem in the network has a unique structure that helps to determine the solution algorithm. The flow variable indicate xij have a coefficient of 0, +1, and -1. Additionally, these variable appear precisely in the two balance equation. Once with the coefficient of the +1 represent the node where the flow originates, and the ones with the coefficient of -1 representing the node where the flow enters. Based on the above characteristic, the general form of the minimum cost flow problem can be stated as follows. The model shown here represents the general form of the minimum cost flow problem. However, we can simplify this model into more simple form that are explained here. This is the shortest path. Shortest path is a special case of the minimum cost flow problem. What is the shortest path? In the real world, the network theory finds a practical application determining the shortest path within a network. In this context, network consists of an area and a region that as a node, and the combination paths connecting them are known as an arc. Any node in this network can be considered either a starting point or a destination. The objective is to define a path between the origin and destination that results in the shortest distance, known as the shortest path within a network. The network covered in this course can categorize into two sections: loopless network and the loop network. In the upcoming section, we will explore each of these networks in more detail, examine their characteristic, property, and application. We start with the loopless network. Loopless networks are similar to the basic network, but in this case, both nodes can act as an arc and can act as an origin and destination node for movement. In the simple shortest path method, computation begins from the origin node and continue toward the destination node. During this computation, each node is assigned as a code M that represents the shortest path from the starting node. The starting node is assumed to have a number of 1, and the end node is the number of n, and the intermediate nodes are sequentially numbered. The algorithm for the loopless network for shortest path problem as follows. In step 1, we start by setting the code of the starting node to 0. M1 is equal to 0. In step 2, calculate the code of node J, which is Mj, using the following equation, where S is a set of nodes that lead to node J, and Dij represents the direct distance between node I and J. In step 3, once the code of the end node is determined, it represents the shortest path, this distance between the starting node and the end node in the network. To find in step 4, to find the shortest path, we employ the backtracking method. We will discuss in the example what is this method. Let's apply the method we find to just learn the shortest path problem from node 1 to 8. in this directed network. The distance between each pair of nodes are indicated as a number above the arch. We can find the shortest path method from node 1 to 8 in the given network using the method we discussed. We start from the code of node 1 as the M1 is equal to 0. We calculate the code for node 2 by adding the M1 plus 4 is equal to node 2. M2 is equal to 4. Moving on to node 3, we have two paths to reach this node. We need to consider the both paths. We have path 1 from this is the path 1 and this is the path 2. So M3, we have the two options for calculating the M3. 1, 0 plus M2 plus 1 is equal to M. M1 plus 3 is equal to 3. The minimum value of the 3 and 5 is equal to 3. So M3 is equal to 3. We continue to this calculation for the other node, and we have the calculation for 8th node in this figure, and we can see that the shortest path from node 1 to 8 is equal to 12. In order to determine the shortest path between node 1 to 8, we use the backtracking method. This involved checking each node j, for example, that meet the condition mi is equal mj minus dij, which help us to identify the node along the shortest path. We start the process from node end node and explore the 3 branch to connect to this. So we get back here. This is the shortest path. We have the two shortest paths. We start from the node 8. 12 minus 3 is equal to 9. So the arc 5, 8 is on the shortest path. So 9 minus 5 is equal to 4. So arc 2, 5 is on the shortest path. Here 12 minus 5 is equal to 7, so it's on the path. 7 minus 6 is not equal to 4, so it's not on the path. 7 minus 2 is equal to 5 is on the path. 12 minus 7 is not 9, is not on the path. 9 minus 4 is equal to 5 is on the path. So it's not, we can eliminate this path. It's not important because we have the other path. So also 5 minus 2 is equal to 3 on the path, and 5 minus 6 is not 0, is not on the path. So we check the all shortest path to find the different option we can move from 1 to 8. We don't consider this path because this is not in the path. So if we find out that the arc 7, 8 is not on the shortest path, we do not consider this path. Okay, by this method, backtracking method, we can find our shortest path from 1 to 8. Let's move on the K shortest path problem. Consider the scenario where the bus driver needs to take a passenger from the origin X to destination Z through the city U, Y, N, M, choosing the shortest path. This is the shortest path. However, during the specific week, there is a thing preventing the city from going to city U. In this situation, the bus driver intends to use the second shortest path as an alternative. This example highlights the need to determine the second, third, or K shortest path problem in the certain case. To find the K shortest path problem, a modification is made on the second step of the simple shortest path problem. This is the modification we should add in the simple shortest path problem to find the K minimum shortest path value. So let's move on an example to find out how we can use this modification for finding the second, third, and the k shortest path problem. Let's find this first, second, and third shortest path between node 1 to 8. Applying a simple shortest path problem, we first obtain the shortest path, and we can find the M11, M51, M21, and so forth. So it's needed for finding the second and third shortest path. We set M12 is equal to 0 as a default. Only one branch enter node 2, so there is no second shortest path. So here, the only branch enter node 2 is 1, 2. So we don't have any option for second shortest path. As a result, M22 is not a value, just a dash. But for node 3, we have two options, node arc 2, 3 and 1, 3. So as a result, we have M11 plus D13 for the shortest path, and this is for second shortest path, M12 plus D13 for the second shortest path, and this is for arc 2, 3 for shortest path and second shortest path. But we don't have M22 here. There is no value. So M11 we have from the shortest path. M12 is equal to 0 as a default, and M21 is equal to 4 as for we find out from the shortest path problem. As a result, we have the 5 minimization of the 3 value. For the other node, we proceed the following. For node number 4, we have the two options, arc 3, 4 and 1, 4. Here, we have one for shortest path and we have one for second shortest path. For arc 1, 4 and for arc 3, 4. We have the 4 value, and the minimization of the 4 value is equal to 6. This is M42. For M62 and M72, we have the following, but for M52, we have only one branch. So like M22, M52, there is no value for these parameters. We have the following for M82. So now we have the second shortest path. We do the backtracking method. In the next slide, we will tell you how we can find. It's similar to shortest path problem. For the third shortest path problem, we said M13 is equal to 0 because only one branch enter node 2, as we have in the second shortest path. There is no option here. So M23 there is no value, but for node 3 we have two options, and for each option or arc we have 3 value, M11 plus MD plus D13, M12 plus D13, and M13 plus D13. So we have this value for the we find out from the first shortest path. We have M12 from the second shortest path, and 1 and 1,3 we set is equal to 0. We don't have any M22 here, is a dash, and also we don't have M23. So here we have only 4 value for the minimization. The minimum value is equal to 5. For M43 we have the same. We have the 6 value. The minimum value of the 6 value is equal to 7. There is no option for M4 and 5.3 as we have here for second shortest path problem. And we do the following, the similar way for M6, M7, M8. So here, this is the second and third shortest path using the K shortest path method problem. The second and third shortest path between node 1 to 8 are determined by examining the node and branch using the backtracking, as we have the finding the simple shortest path method. In this case, there are 2 possible answers for the second shortest path. this option and this option, and one option for third shortest path. We show the shortest path in the network here. We have two options for shortest path or the first shortest path. We have two options for second shortest path here. And finally, we have the one option for third shortest path by tracking methods. In the loop network, there are arcs that create loops, allowing the movement between nodes in both forward and backward direction. To find the shortest path in such network, two methods are commonly used. The first method is the Dijkestra method. This method is named after its inventor. In the Dijkestra methods, two codes are assigned to each node. The first is the M sub I. This represents the shortest distance of node I from the origin up to the current step of the algorithm. It is known as a temporary code since the shortest path may be updated in a subsequent step. M capital sub I. This represents the shortest distance of node I from the origin and is referred as a permanent code. Once assigned, this code will not be updated with the shortest distance in the following step. The actual method can be summarized in the following step. Step 1. Start by assigning the permanent code of 0 to starting node. M1 is equal to 0 because node 1 is a starting node. Assign the temporary code to the node adjacent to the node that already have the permanent code using the following formula. Temporary code of node J, M sub J, is equal to minimum of the permanent code of node I plus Dij. Here, Dij represents the direct distance from node I with the permanent code to the adjacent node J with the temporary code. If a node already has a temporary code, it is compared with the new temporary code and the smaller value is chosen. Among the all nodes with the temporary code, the node with the smallest code is converted to a permanent code here. The process continues until by assigning the temporary codes to the node adjacent to the node with the newly assigned permanent code and so on. In step 3, we stop the algorithm when the end or destination node receives the permanent code. The value of the m sub n and the number of nodes represent the shortest distance between the end node and the starting node. In step 4, we find the shortest path. We use the backtracking method with the following relationship. Here, m sub I is equal to m sub j minus d sub ij. If this relation holds, arc ij is on the shortest path. To better understand this step, let's solve the following example. Here, this is the example, and the number over the arc is the cost. We are going to find the shortest path using the Dijkestra method from 1 to 7. Here the solution we find in the optimal shortest path between 1 to 7. We start by assigning the permanent code to node 1, where m sub I is equal to 0. Since node R has received the permanent code, we assign the temporary code to its adjacent node. So here, node 2, 4, and 3 are the adjacent node to node 1. So we assign the temporary code to these node. M2 is equal to 3, M3 equal to 7, M4 is equal to 5. Among the temporary code available so far, these 3 code, the minimum value is 3 for M2. Therefore, the temporary code of node 2 is converted to the permanent code. We assign the temporary code to the node adjacent to node 2. Node 2, we have 2 adjacent nodes, node 5 and node 4. Okay, node 4 already had a temporary code of 5 here. From the last step, we know that a node 4 is equal to 5, the permanent code of node 4. But here we find that the node 4, the temporal code of node 4 is equal to 4. So the minimum value of the 4 and 5 is equal to 4. Then we update the temporal code of node 4 to 4. And we find the minimum value of the temporary code available here. We have 3 temporary codes so far, 7, 4, and 30. 4 is the minimum value. As a result, node 4 received a permanent code with value of the 4. This process continues in this manner, assigning the temporary code and updating the input accordingly. The diagram here summarizes the result of the different step of the algorithm, and you can see that the node 4 has the permanent code and defining the shortest path. We find the shortest path from 1 to 7 with the value of the 11. Here we can see that the node 5, no permanent code for node 5. To find the shortest path between node 1 to 7, we can use the backtracking method. We follow the similar approach in the network without loop in the earlier slide. We start by examining the arc and node along the shortest path. Arc 5, 7 is not on the shortest path because M5 is not equal to 5. There is no M5 because we do not have the permanent code for node 5. As a result, arc 5, 7 is not on the shortest path. But arc 7, 6, 6, 7 is on the shortest path because M6 is equal to 8. No, arc 4, 6 is on the shortest path because M4 is equal to 4. Arc 3, 6 is on the shortest path because M3 is equal to 5 and so forth. Here you can see that the arc 1, 3 is not on the shortest path because M1 is not equal to minus 2 is equal to 0. Here arc 1, 2 is on the shortest path and also arc 2, 4 is on the shortest path. As a result, we have the two shortest paths here from 1 to 7. And in this figure, you can find the shortest path. The one shortest path is 1, 2, 4, 6, and 7, and the other is 1, 2, 4, 3, 6, and 7. All both shortest path has a value of the 11. The comprehensive shortest path method is a way to find the shortest path in a network. The Dijkestra algorithm is the simplest method for this, but it has a limitation. It only determines the shortest distance between starting and end node in each step of the Dijkestra algorithm. However, with the comprehensive shortest path methods, we can calculate the shortest path between all nodes in the network. If the network has an m node, we start numbering them from 1 to m with the starting node as 1 and the ending node as m. The rest of the nodes are numbered in the ascending order from the starting node to the end node. In this method, we use the two matrices, one for distance as d and another for path p. The value dij represents the distance between node I to j here, while pij represents the path from node I to j. If there is no direct path between two nodes, we consider the distance between them as infinity, and mark the path with the dash sign. We will see in the example. It's important to note that the distance from one node to another, which is dij, may not be the same as the distance from the return journey, which is dji. For example, D1, 2 here represent the distance from node 1 to node 2. Similarly, the P1, 2 represent the path from 1 to 2. At each stage of this algorithm, which is j is equal to 1 to m, we select the node j as an intermediate node here. Then we calculate the route between any two nodes excluding node j. If the newly calculated distance is shorter than the previous distance, for example here, we update with the here the intermediate node, which is j, the distance is shorter than the current distance. So we update the distance between node I to k. Otherwise, we keep the previous distance. We have the following result in the P matrix. So if the intermediate node, which is node J, cause the shortest path between I to K, so we update matrix P as Pij. Otherwise, we do not update. Let me illustrate with an example to provide further information. Consider this example with the 5 node and some arc, and the distance between each node as a number above the arc. Use the comprehensive shortest path method. Find the shortest path between all nodes in the network. We start with the D0. So here D0 and P0. For example, from 1 to 1, the distance is equal to 0. From 1 to 3, the distance is equal to 3, with the intermediate node is equal to 2 here. From 1 to 5, 1 to 3, 1 to 3, the distance is equal to 5, and the intermediate is 3. 1 to 4, 1 to 4 is 5, but 1 to 5, there is no direct distance between 1 to 5. So the distance d1, 5 is equal to infinity, and we use the dash line. We do the same for the other nodes in D0 and P0. At stage 1, with the intermediate node, which is node 1. In this matrix, the distance between node 2 and 3 is marked as infinity here. However, we consider the path through the intermediate node 1. The distance between node 2 and 3 become 9. So there is no direct path between node 2 and 3. But if we consider the node 1 as an intermediate node, we can update the distance between node 2 and 3 by 9. 3. This is 4. This is 5. 4 and 5 is equal to 9. Since this intermediate path is the shortest, the distance in the matrix D0, which is infinity, we replace it with a new value. So we do change the path. The same is done for the other nodes here. For example, we can update the distance between 2 and 4. So there is no direct path between 2 and 4. But if we consider the node 1 as an intermediate node, we can update it. So here, the new update value is 9. D25 is not updated, but D32 we can update because there is no direct distance between 3 and 2. Okay, there is no direct distance. But if we consider node 1 as an intermediate path, intermediate node, we can update it by 7. So we do the same is done for the other, for step 2, which the node 2 is the intermediate node. You can see that. And in this step, we observe the change in the distance and the road matrix between node 1 to 5. Okay, this is node 2. Okay, this is node 1. So as we resolve, we have the 2 change in the D matrix and the P matrix. This is node between 2 and 3 and 2 and 4 with the value of 9. And the intermediate node in this metric, which is pass matrix, is 1. In step 2, we use the node 2 as the intermediate node. So as here you can see that we have some change in the D matrix and P matrix. So we have 5 change in the D matrix and the P matrix. So we have the same, we have the updated D matrix and P matrix for step 2, which is node 2 is the intermediate node. We do the same for stage 3, where the intermediate node is node 3, and the updated value for D3 and P3 is as follow. And for step 4, where the intermediate node is node 4, we have 1 change. This is the new updated value for D matrix and P matrix for step 4. And we go to the step 5, where the intermediate node is node 5. At this stage, we observe the change in the distance and route between node 2 and 3. Node 4 and 3, we have 2 change. So here, 1 change between 2 and 3 and 4 and 3. Consequently, the metrics for this step, which represent the final metrics, are as follow. So D5 is the final matrix, and P5 is the final matrix for P. The algorithm concludes, and we can obtain the shortest path between 2 nodes from D5 matrix. Likewise, we can trace the corresponding path using the P5 matrix. For example, in D5 matrix, the shortest distance between node 2 and 4, node 4 is equal to 9. By examining the P5 matrix, you can find that the shortest path between node 2 and 4 include node 1. And the shortest path between node 1 to 4, here 1 to 4 through node 4 itself. So it means that the shortest path between node 2 and node 4 is 2, 1, 4. So by doing this method, we can find any shortest path between to any arbitrary node in the network. You may ask for more exercises to practice. Check out my website, where you can find the variety of exercise. You can discover the exercise covering the different subjects in operation research, network optimization, linear programming, integer programming, nonlinear, and so on. So give it a shot. Thank you so much for watching us. If you have any if you have any question, you can send one email by optimizationcity@gmail.com, or you can fill out the contact form in the website, where www.optimizationcity.com. Thank you so much, and goodbye for now.